The goal of this video is to present and understand physical information verbally, pictorially, graphically, and mathematically. It is generally important in physics to be able to present information in a number of different ways. Besides the flexibility this skill provides for sharing information with others, attempting to recast information in a different form often reveals truths that were not immediately apparent otherwise. Consider this simple sentence: a skydiver falls. It shouldn't be too difficult to imagine what this may look like. From this simple statement and image, what information can we gather? We know our skydiver has a velocity downward, so next to our quick sketch of our skydiver, we can label an arrow showing this velocity. We also know that the skydiver should be accelerating downwards. We are going to go ahead and assume that we can ignore air resistance for the purposes of this video. In this case, the acceleration of the skydiver should be that of gravity, so we can label that too. It is straightforward to diagram the motion of the skydiver. At some initial time, the skydiver is at some initial height. At a later time, the skydiver is lower than she was previously. The acceleration should still be that of gravity, but the velocity should be greater than it was before, so we'll make that arrow larger and adjust its label. At a later time still, because the skydiver is now moving faster than she was before, she will have traveled even further downward. Again, her acceleration will be unchanged, but her velocity is incrementally larger. Now we have a diagram depicting the same information as the sentence above it. We could also represent this information mathematically. Generally, objects moving under constant acceleration obey this equation of motion: delta x equals v naught delta t plus 1/2 a delta t squared. For this case specifically, the height of the skydiver could be represented by h, and the acceleration would simply be plugged in as g. This would be the equation of motion for our skydiver, therefore this equation also represents the information contained in the diagram and in the sentence. But to a physicist, this statement is of more practical use. Finally, we could also represent this information on an xy axis. On our horizontal axis, we will have time. The height of the skydiver as a function of time, according to this equation, is quadratic. So a quick sketch of the height of the skydiver as a function of time would look like this. The velocity, on the other hand, will be linearly increasing in the negative, downward direction. The velocity of the skydiver as a function of time should look something like this. The acceleration of the skydiver never changes, so the acceleration as a function of time will be a horizontal line. Let's say we had additional information in our first statement. Our skydiver fell from rest, and for only 2 seconds. What does this do to our other representations of information? First off, because we are starting from rest, we can get rid of this first velocity. Second, we can plug in the values we have into our equation. We'll call the initial position of the skydiver 0, the initial velocity is given as 0, the time interval is given as 2 seconds, and the acceleration due to gravity is 9.8 meters per second squared. Plugging these values in yields a position of negative 19.6 meters, telling us that after 2 seconds our skydiver has fallen 19.6 meters. We can also plug these values into our plot, giving quantitative value to our sketches versus time. Let's consider another example. We are told that a car traveling west at a speed of 20 meters per second slows to a stop with a constant acceleration of 5 meters per second squared. We'll begin our drawing by labeling our directions: north, south, east, and west. We will use eastward as positive and westward as negative. We'll sketch in the car as is described at the beginning of the statement, and label the information we have. We'll start our timing here, so we label our initial time as 0 seconds. The initial velocity of the car is 20 meters per second. We'll make this a negative 20 meters per second since the car is traveling in the westward direction, which we have defined as negative. The initial position of the car is not given, but we can assign this position as 0 meters and measure the displacement of the car from here. The car slows to a stop after traveling some distance to the west, so we'll sketch the car in again at this final case and label the same variables. The time the car comes to a stop is unknown, so we'll use the placeholder t sub f. The car comes to a stop, so we will label the velocity v sub f as 0 meters per second. The distance the car traveled is unknown, so we will leave the placeholder x sub f. The acceleration of the car between t0 and t sub f is always 5 meters per second squared, so we will label a as 5 meters per second squared. Notice the labeling of the acceleration is positive to ensure it works against the initial velocity so as to bring the car to a stop. We can create a diagram representing this information. We'll start by labeling a general x-axis. Initially, our car is at the position x0 and has a velocity to the west of v0. Some time later, the car will have moved a distance to the west, and will have a slightly smaller velocity. A little later still, the car has moved not quite as far west, and has still a smaller velocity. Eventually, the car will have a speed of 0 meters per second at a position x sub f. From here, we could create both the mathematic and graphical representation of this information. The general equation of motion is here. X sub f equals x naught plus v naught delta t plus 1/2 a delta t squared. We'll also be using the simplest definition of acceleration. V sub f equals v naught plus a delta t. The general shapes of our plots should be the following. The position starts at 0 and quadratically approaches a constant value in the westward, that is negative, direction. The velocity starts from negative 20 meters per second and linearly approaches 0 meters per second. The acceleration is a positive 5 meters per second squared always. From here, we could go a step further and plug the given values into our equations. An initial position of 0 meters, an initial velocity of negative 20 meters per second, an initial time of 0 is assumed, and an acceleration of 5 meters per second squared. The equation to the right quickly reduces into a value for the time at which the car comes to a rest. By these numbers, the car will take 4 seconds to come to a stop. So we can plug in the value of 4 seconds into t sub f in the equation at the left, which will determine a value for the position at which our car comes to a rest.